As you may have guessed by the title, this talk is also about the Camerarius Digital project, which my colleague Alexander Hubert has already explained to you in detail yesterday. The focus of this talk is one of the three main parts of the Camerarius Digital project. In this talk, we'll focus on the transcription of 20,000 pages of historical printings, which have been written by Joachim Camerarius the Elder. The goal of the project is to make the oeuvre of Joachim Camerarius available in digital form and searchable and citable for the public. In this talk, we'll first have a quick look at the source data and the unique challenges. Then I will introduce you to our fully automatic workflow used for this mass transcription project. Then we'll have a deep dive into the learning techniques used in our project. Especially, we will have a look at the text detection, layout recognition, and the optical character recognition for both Latin and Greek. In the end, I will give you a quick live demonstration where I will present you the correction tools for the layout and the optical character recognition for Latin and Greek. Here on the slide, you can see two examples from the Camerarius Digital corpus. For this project, we haven't digitized any pages ourselves, but instead, we have gathered the page images from the repositories of publicly available images from libraries. Therefore, we cannot control the quality of the images. Sometimes the quality is really good, but also in some cases, the image quality is not perfect. For example, as you can see here on the right, there might be a significant amount of bleed-through from the back of the page. Also, sometimes the images have very low contrast, are skewed, which means that the pages are slightly rotated so that the text lines are not perfectly horizontal, or the images might be warped. This happens because these images are created by photographing or making photos of the book. And because the book is not perfectly flat, you will then have a bend in the text lines. In addition, because these are historical printings, there are often difficult layout elements present. For example, as you can see here on the right side, there's marginalia, which in this case are astrological symbols. There might be page numbers, header elements, catchwords and signature marks, but also dropped capitals at the beginning of the text lines. In addition, because the printings from Joachim Camerarius were done by a lot of different printers at different locations, there's no uniform layout or font style. As you can see here on the left side, the font in this document is in italic, and the font in the right document is a recto font. The most difficult challenge is that the texts are not written in just one language. The texts are written in a mixture of Latin and Greek, and sometimes, as you can see here on the left side, there are individual Greek words or lines written inside of the Latin text. All in all, these are not the best conditions for an off-the-shelf OCR solution, and that is why we opted to build our own pipeline based upon already existing components, which is perfect for this project. Let me quickly introduce you to the workflow for recognizing historical documents. First of all, we have to gather the input images. These are then uploaded into our automatic system. In the first step, the images are pre-processed, which means they are deskewed and optional dewarped. We do not dewarp all pages, only when it's necessary, because it might reduce the quality of the images. Then comes our automatic layout recognition, text detection, and OCR pipeline. The first step is the text detection and layout recognition, where the goal is to identify individual text lines and other elements on the page, and these are then fed into the OCR in order to be transcribed. After the OCR, there's also an automatic post-correction system, which is based on a dictionary, which aims to quickly identify potential errors in the OCR. After this is done, there is also a manual correction process because we want to produce very high quality transcriptions. and the previous steps might not have a perfect output. The main focus of this talk will be these two steps in the middle, which for this project, we use machine learning in order to automate these steps. And this is also the topic of my PhD thesis that I'm currently writing at the University of Würzburg. So let's see how we can apply machine learning in order to detect text and the layout of historical documents. As you can see here, one possibility is to identify text by recognizing the baselines of the text. The baseline is the virtual line under a text line where each individual character sits upon. Now, labeling this by hand would, of course, not be very efficient, and because we have to do it for 20,000 pages, it would take a very long time. So we opted to use machine learning in order to train a computer vision model. And this computer vision model can then label individual pixels in our image that form the baselines of the printed text. Let's have a quick look at how this machine learning process works. First of all, we have to start with a training data set. In our case, these could, for example, be a collection of page images. And for this training data set, we also need correct annotations, for example, baseline annotations. This data set and the correct annotations are typically created by a supervisor, which is, for example, a human annotator. For the task of the OCR, this might not be complete page images, but individual text lines, and the annotations for the OCR task would then be the correct transcriptions for these lines. Such a data set is then fed into a machine learning algorithm for training. During training, we train a model on our training dataset with the correct annotations to predict these annotations for the dataset that we've given it. Then the model learns to predict annotations for new data, which we can then feed to the model in a prediction step in order to get hopefully correctly annotated data for the new data. There are a couple of key points that I want to state here. The first is that it's very important that the training data has to be suitable for the prediction task. So if we want to predict on historical documents, the training data set should also be comprised of historical documents. In addition, the more training data you have in general means that your model will be better. But even though you might have perfectly suitable training data and a lot of it, still the model can make mistakes. So it's important to think about either implementing a post-correction step or to have a manual correction step at the end. Let's look how we annotated the data for our baseline recognition model. Here you can see an example page where the baselines are annotated in red. At the beginning of the project, we trained our model on the read-bad dataset, which is a publicly available dataset. And it is comprised of a lot of different printings as well as handwritten texts from a lot of different sources. We took approximately 1,100 images from this data set with baseline annotations and trained a base model on them. Then we fine-tuned a model on customly annotated data, like you can see here. We used approximately 500 pages. And during this fine-tuning step, which is effectively another training step for the model, but in this time we used data which is much closer to the data that we actually want to run the model. Let's have a look at the architecture of our baseline detector. So first, the baseline detection is what's called a pixel classifier for semantic segmentation, which means that the model labels individual pixels in the input image. In our case, the labels can be baseline, divider, or background. The model is structured in what's called a unit architecture, which gets its name from the shape of the model, as you can see here on the left. The model is comprised of two main parts: the encoder on the left side, which takes the input image of the document as an input, and then applies convolutional layers and pooling layers to it. As we go deeper into the model, we build feature maps at each individual layer, and these feature maps learn to recognize increasingly complex features as we go down in the model. Then the right side of the model is what we call the decoder, and its job is to upsample the feature maps and combine them with the lower level feature maps from the encoder in order to produce an output segmentation map. It's important to note that we found that this model generalizes very well to unseen data. So it would not even be necessary to train the model or fine-tune the model on our own data, because just using the read-back data set would have been sufficient to produce a somewhat good model. But of course, by fine-tuning, we could improve the performance. And over the course of this project, we added more and more training data to our model in order to improve it even further. At our chair at the University of Würzburg, we also use UNet models for a variety of different tasks, such as detecting polyps in medical images, but also to recognize symbols, for example, in musical documents, or to recognize handwritten annotations in tables. Okay, let's have a look at what we have so far. We have built a machine learning model that can recognize the baselines on our document, but for the OCR, it's important that we generate text line polygons, which we can then feed into the OCR. For this, we use a graph-based algorithm for line polygon generation, which is a bit too complicated to go into detail right now, but you can think of it. It takes an individual baseline and the baselines in its immediate context, and then it combines them and forms the line polygons. After we have these text line polygons, there's still some important parts missing. For example, we do not have annotations for the dropped capitals, and we also don't know what type of text line we are dealing with. So for example, we do not know if it's a headline or if it's a marginalia or a catchword and so on. Let's first have a look at how we solved the issue with the drop capitals. For this, we used a different deep convolutional neural network, which is called YOLO, you only look once. YOLO is a deep convolutional neural network that's used for many different detection tasks. Typically, that's object detection in photographs, but it can also be used, for example, for tracking objects in videos or for pose estimation in photographs of humans. In contrast to the baseline semantic segmentation model, we use YOLO for the object detection task, which means that it directly predicts as bounding boxes for dropped capitals and images. During the project, because we started off with just our baseline recognizer, and then we corrected the data and labeled also the dropped capitals and images, and we then used this data during the project to gather training data for YOLO. So our YOLO model was finally trained on all of our corpus, as well as on synthetic training data. And then these predictions from the YOLO model will then also be used in the next step, which is the rule-based layout recognition. So we are still missing the annotations for the individual types of text lines. And for that, we implemented a rule-based layout recognition system, which utilizes background knowledge about the typical position and relations of different elements on the page. So in this layout recognition system, we define a rule book. So for example, you could define a rule for marginalia, which could consist of, or which could be described as if a text line is to the left or to the right of the main text, and it is next to a line which has the line type paragraph, then this line should be classified as marginalia. Or for example, you could define a rule like for the line number, where you say if this text line is a marginalia and it is numeric, then it should be classified as a line number. For example, for the page number, we could define a rule that the text line has to be on top of the page, so there's no other paragraph above it. And for the header, we could define a rule that it's on top of the page and it's centered and it's not numeric, unlike the page number. It's important to note that our rule-based layout recognition system runs in many iterations. because the output of our baseline model must not necessarily be perfect. For example, a typical failure case is that the marginalia and the main text is combined in a single text line. And therefore, in this rule-based system, we also have special rules for this case. And these rules would then separate the marginalia from the main text line and split it into two individual text lines. And then we would do another iteration of our system in order to classify the newly generated lines. The system in general works so each rule in general is applying a score for each text line element, and the final class in the end is chosen by the rule that has given the text line the highest score. This system is what we would call a domain-specific approach, which means that it only works for this kind of printings. So it doesn't generalize to different, completely different layouts. The layouts have to be similar to what we have written the rules for. But in the future, we also aim to be, for example, able to learn the rules, just giving the system a few examples, so we can then use the system on a variety of different data. For example, we also want to use the system to recognize tables and receipts. Okay. Now that we've talked about the layout recognition, let me introduce you to our optical character recognition system. The task of the optical character recognition is that given the input image of a text line, the system should transcribe it into a digital form, which we can then edit on the computer. For the OCR, for this project, we use CRNN, which is a convolutional recurrent neural network. And you can see the architecture of the CRNN here on the right. The left part here, in the beginning, or the first part of the CRNN, is similar to what we had in our unit. We have the input image here, and then we calculate feature maps in several different layers from this input image. These feature maps are then converted into a feature sequence. You can think of it as for each vertical slice in the input image, one of these arrays of features is present in this feature sequence. This feature sequence is then fed into an LSTM model, which aims at modeling the context between adjacent feature arrays so that we can carry context from one letter to the next. The LSTM will then produce an output for each individual slice, vertical slice of the input image. So for example, as you can see here, on the left side of the input image, there is nothing. Therefore, the LSTM predicted an empty token. Then there is the letter S. Therefore, we predict the letter S, and so on. And this representation is then concatenated to the final transcription, which in this case would be state for the input image. Okay, now let's look how we actually apply this model for our Latin OCR. The goal for our OCR is to produce a diplomatic transcription, which means that we want to stay as close as possible to the original. That also means that we want to keep all special characters, such as, for example, diacritics or ligatures, as you can see here, or even the astrological symbols that I've shown you earlier. This also means that we want to keep all of the Greek letters in the transcription. But there's a slight problem. Ancient Greek is very difficult, so you need specialists to correct Greek OCR and to annotate training data for the Greek OCR. Another issue is that there's an overlap between the Greek characters and the Latin characters. So if you if you would train a mixed model, it might be possible that a word that looks like Latin, that the model is then actually transcribing only using Latin characters. And there could also be a bias because most of our data or most of the text is actually written in Latin. So the OCR model might actually be biased to produce Latin letters with a higher probability than to transcribe the Greek letters. Therefore, for our project, for the first years, we only did the Latin OCR, which means we were training a Latin OCR model, and we are using replacement characters for Greek words in the Latin corrections. Okay. Let me now present you our workflow for optimizing the Latin models. So we first started off with a generic Latin OCR model, which we trained on the data that we had available and also on some of the first annotated data from the Camerarius project. Then we trained the generic Latin model. Now the workflow looks like this, that we take the whole book as an input and feed it into our automatic system. The first step is that the whole book runs through our layout recognition. Then it runs through the OCR using the generic Latin OCR model. Afterwards, human annotators correct some of the pages. So for example, the first 10 or 20 pages could be corrected. We then take these corrected pages and fine-tune our Latin OCR model to be more suitable for this book that we are currently transcribing. This was especially useful in the beginning where we did not have enough training data for certain font styles. So by fine-tuning, we could quickly improve the quality of the OCR. We then use the fine-tuned model to predict the, or to run the OCR again on the remaining pages of the book. And then this process repeats, which means that we correct again some of the newly OCR'd pages, we fine-tune again, and we run the OCR again for the rest of the book. What you can see here is that this actually produces a positive feedback loop. That means that the more we correct, the better our OCR is going to be, especially for the remaining of the book. In order to improve the OCR in general, we also regularly train new, better generic OCR models using all of the corrected material that we have gathered over the time. Okay, this was the workflow for the Latin OCR. And last year, we also started with correcting the Greek OCR for this project. But it's important to note that we only do the Greek OCR after a book has been fully corrected in Latin. Let me explain to you now how we do the Greek OCR. If we look at the output of the CNN, as you have seen on a couple of slides before, the output of the CNN actually aligns with the input image because the CNN also predicts these empty characters, right? So for each vertical slice of the input image, we get one character as an output or an empty, which also means that our replacement symbols in the Latin OCR align perfectly with the Greek words in the text line. Therefore, we can utilize our Latin model to detect individual Greek words, or in the case that the whole line is Greek, we can also, of course, detect whole Greek lines by the Latin model. And then we feed these cutouts that we can detect using the Latin model into a specialized Greek OCR model. Right now, we're using a Greek OCR model that has been trained on full Greek books. But in the future, we will also use individual words which are annotated using this process in our training. Okay, let me quickly show you some of the evaluation results of our method. So for the text detection using the baseline and the line polygon generation, we get a 99.9% per pixel F1 score, which means we can detect most of the text on the page in the corpus using this method. If we look at individual text line instances, for example, I've already talked about before that sometimes the model might merge the marginalia and the main text into a single line. And of course, sometimes our rule-based layout system doesn't recognize this correctly. So we get a slightly lower score here of just 99.0% F1. For the layout element recognition on very simple and regular layouts, we can achieve near perfect accuracy with 99.9%, but for more complicated layouts, the accuracy drops and we only achieve 97.7% F1 score. So that would, for example, be printings with a lot of short marginalia or, for example, with tiny page numbers at the top, which are sometimes not recognized correctly by our system. For the OCR, right now we have generic OCR models which have been trained using approximately 8,000 pages of annotated training data, and we get a character error rate of 0.55% across the entire training data. For the Greek OCR, we've again trained the models on single books, and for that single book, we achieved a character error rate of 0.65%. But this is not representative for the whole corpus, and there still needs to be a lot of work done in order to get this kind of character error rate across the entire Camerarius corpus. Okay.
1 minute left.
1 minute, then I can quickly show you a live demonstration of our.
Let us say 2.
Okay, a quick live demonstration for our correction tools. So here you can see our editor where we are correcting the segmentation in Latin OCR. As you can see here, there is, because of the stamp, an error in the baseline analysis and the layout segmentation. So we would now have to go in and manually annotate this text line. Then we can automatically rerun the reading order. I have to first set this to heading, which was also not correctly detected because of the stamp. I can then run the reading order, and then we can go into the text correction view where we can see the correction interface. And this is the thing that I hinted at the beginning, which is the automatic post correction for the OCR. And you can see it in action here because you can see here's the cutout for an individual text line and the OCR result. And the OCR result is colored in different colors. So for example, here, the post correction determined that this word is available in 2 different forms in the dictionary. One version is with just an I, and this one is with an I and J at the end. Here, the dropped capital was not recognized correctly by the OCR. So if I'm correcting it, you can also see that now the post correction hints the user that this line and the next line actually form a single word. So we can right click and put in a special character in order to tell the system that now these 2 text lines should actually be concatenated. This is important for the user if he wants to search for this word so that it can be found. In case of an OCR error, as you can see here, the automatic post correction based on the dictionary will also give you the correct word that you can just click on, and then it's automatically corrected. Or, of course, you could manually go in and correct it. And for the Greek OCR, we have this correction tool. Well, I just wanted to show you this tool where you can do the Greek correction, but as you can see, it's actually very, very simple for the correction of the Greek tasks. So thank you very much for your attention. And if you have any questions, I'd be happy to answer them now.